Good afternoon. My name is Kyuwon from Sungkyunkwan University. I will be presenting our work called RustSan, which retrofit the address sanitizer for Rust. Rust is emerging as a safe alternative to traditional system programming language such as C and C++. Thanks to its built-in language system such as borrow checker or ownership system, the Rust provides the memory and type safety guarantees. The rise of Rust's popularity can be seen through its inclusion in the Linux kernel and GitHub unique commit trend for languages. And we expect that this trend will continue. However, Rust safety guarantees are not free. If you have programmed in Rust, you probably know what I mean. Rust forces the programmers to participate in the strict language semantic, which can be cumbersome in times. Therefore, programmers sometimes turn to the dark side, the unsafe Rust, to escape those strict compiler rules. In practice, unsafe Rust is necessary for a finer touch with low-level interaction with system, but also unsafe is often used as an easy shortcut that trades safety for convenience. The unsafe bring back the risk. Memory safety-related CVEs in Rust-based program have been continuously reported. As can be seen in description of the reported CVE and also in the previous work, unsafe is the predominant source of memory safety problem in Rust programs. For this reason, the conventional methods for fighting memory safety bug have also been embraced by Rust community. For example, the Rust toolchain integrated the built-in option to build their application with AddressSanitizer ASan. Also, many Rust CVEs that stem from memory error have been discovered through sanitizer-assisted fuzz testing efforts. And here's the motivation for our work. Our observation is that most of the Rust program still retains safety guarantees even with the presence of unsafe Rust. The question is, can you accurately identify such safe parts of a program to vindicate them from costly sanitizer checks? As we'll exemplify with the following example, safe code can be divided into two types. On the one hand, it never be affected and interact by the unsafe and retains its safety. On the other hand, it may be affected by unsafe and becomes unsafe too. We call the later one as a false safe code. Let's find out how the false safe sites arise with the code example. In line 3, there is an unsafe block with a red box, but it just makes pointer arithmetic and typecasting. So the unsafe block itself do not make any illegal memory commitment, but the inconsistent pointer return to the line 7 and dereference in line 8. The pointer dereferencing sites belong to the safe, but the pointer value is affected by unsafe, so that it may commit illegal memory access. This is an example of false safe. The unsafety propagation is not over yet. The dereferencing itself is dangerous, thus the load returns an inconsistent value. Similarly, there is no telling how far this contamination can reach. Let's summarize our terminology. Memory access sites that do not belong in an unsafe block and are not connected with an unsafe block with the data flow relations are safe. In contrast, the access sites inside the unsafe are called unsafe sites, and the objects that are modified inside an unsafe block are called unsafe objects. False safe memory access sites are characterized by interaction with unsafe objects. As in the code example, these sites can potentially commit illegal memory operations. Lastly, we have another classification for objects that we called overlapping objects. Overlapping objects are a small number of safe objects that overlap with unsafe objects in the point-to set of false safe sites. Due to the context-insensitive nature of ASan checks, we allow false safe sites to access this small set. our work, RustSan, retrofit the address sanitizer to pinpoint to potentially unsafe memory access while lifting costly ASan checks on others. We use static analysis over LLVM and Rust MIR level named cross-IR analysis to identify all unsafe and false safe. We also extend ASan's shadow memory model to enforce different policy for safe, false safe, and unsafe sites. Here is the RustSan's overall design. We have two components, cross-IR analysis and retrofitted shadow memory for RustSan's access validation model. Let's break it down component by component. Our analysis starts with the Rust-specific IR, MIR, because the Rust semantics such as unsafe are consumed in the Rust MIR level of the compilation process. So we developed an analysis at the MIR level and propagated the result as a form of the instruction metadata into the LLVM IR phase. Our Rust MIR analysis identifies MIR statement that commit change to variable as they are birthplace of unsafe object by definition. Then we propagated the distilled information onto the LLVM phase by tagging the corresponding LLVM IR instructions. This way, we seamlessly bridge the two different kinds of IRs toward the objective of RustSan. With the metadata passed on from the MIR analysis, our LLVM analysis then perform a data flow analysis to identify all unsafe object allocations. We apply pointer analysis based on the state-of-the-art tool, SBF, to find the false safe sites that may access the unsafe object and identify the remaining sites as safe. Furthermore, we traverse the data flow graph again and identify all overlapping objects connected with false safe sites. With the analysis result of site and object safety information, our LLVM compiler paths perform instrumentation over object allocation sites and their memory access sites accordingly. So in original ASan, the shadow memory color check is binary. However, RustSan colors the object with 3 safety levels based on the sites and object safety that we explained. Safe object color is red and overlapping object color is pink. For this reason, the RustSan extends the ASan shadow memory implementation to reflect our Rust safety model. With the object colored accordingly to safety, we also apply instrumentation to access sites according to their safety. The safe sites are freed from unnecessary sanitizer checks, providing a significant performance increase during runtime. With color-aware checks, the full safe sites can access overlapping object and unsafe object, but it cannot access the safe object. Similarly, the unsafe sites can only access the unsafe object, but it cannot access any other type of object. For the evaluation, we collected all Rust memory safety CVEs and reproduced them with RustSan to show the detection capability of RustSan. We also collected the 20 real-world applications from Crate.io and built their built-in benchmark with ASan and RustSan. Among many other statistics presented in the paper, the diagram shows the ratio of safe and false safe sites identified by RustSan in 33 popular crates. The number shows that RustSan identified 93% of code on average as safe, and it means RustSan eliminates checks on the vast majority of memory access sites. We also evaluated the detection capability of RustSan. We surveyed all Rust CVEs from advisory database and picked out that ones that could be reproduced with ASan. Then we performed a detection test with RustSan on the same samples. Even with 94% of checks removed, RustSan successfully detected all CVEs that ASan can detect. Furthermore, 66% of them are detected as fail-safe sites, which shows the effectiveness and accuracy of our cross-IR analysis. These are the cases of memory errors that are born within unsafe, but manifest themselves in the fail-safe sites are parts of the Rust. Performance gain through RustSan in popular Rust crate was measured to be around 62% on average. The performance gain varied across different crates. This is because the gain is from reduced encounter with shadow memory checks. In other words, the performance increase will be dramatic if a high ratio of safe sites now freed from the sanitizer checks is encountered during the execution of the given task. If the executed sites are mostly unsafe or false safe, then performance increase may be limited. Among our benchmark targets, RustSan show the dramatic improvement as in case of UUID or Adler, or little to no improvement in the case of VecDQ. In the figure, the red line represents the measured decrease of runtime shadow check encounters compared to ASan. The performance increase and the red line are very highly correlated, showing the validity of RustSan's design. There are a lot of details that we could not convey in this talk, so if you're interested, please check out our paper. Thank you all for your attention, and I would be happy to answer your questions.